Hello everybody. In this class we will deal with propositional equivalence. What does it mean by propositional equivalence and how to prove that two propositions are equivalent, and we will see some laws to prove this equivalence. There are some laws that have been laid out. First of all, let us define what is propositional equivalence. If you have got two different compound prepositions, say compound prepositions like and, there are two compound prepositions, isn't it? P or Q is one compound preposition, and another compound preposition that we have got here is not of, not P and not Q. These are two prepositions. What we are saying is that when do we call these two prepositions are equivalent? What I mean is that here we have got two prepositions which are syntactically different. Definitely they look like different, but they may be semantically equal. Like in English we have got, when we say Rama killed Ravana, and then another statement we say Ravana was killed by Rama, both are actually syntactically different, but they are semantically the same. Here what we want to say is, though we have got two compound prepositions like P or Q and another compound preposition like not of, not P and not Q, though they are syntactically different, are they really semantically different, or they are the same? How do you say these two are the same? How do we say is, generally for all possible values that P and Q can assume, if both of them will give you the same truth value, then we say these two statements are semantically equal, or two prepositions are equivalent. We will take with an example and see it. When do we say exactly two prepositions are equivalent? Before that, we will define some of the things like tautology. We say a statement, a compound preposition, a tautology, if it always results truth as its true value, immaterial of what its constituent atomic prepositions assume values. What I mean here is, let us see this simple example. So we all understand P or not P is definitely a compound preposition. So when do we say this a tautology is, whatever the values that P assumes, whether P assumes true or P assumes false value, this compound preposition, that is P or not P, should always be truth, should always have truth as its truth value. What I mean is, if we really construct a truth table of this compound preposition, this is P, and this is this compound preposition that we are talking of. So what values, what truth values that this atomic preposition here, that is P, can assume? It can assume either true or it can assume false. Only these two truth values that it can assume. In both the cases, if this compound preposition is taking true as its truth value, then we say this compound preposition, that is P or not P, is a tautology, otherwise not. Let us see what this compound preposition takes when P takes T as its truth value. Then it takes T or not of T or not of T, that is T or false. We have seen that by the very definition of R, T or false is true, that is T. We will see what happens when P assumes the value of false as its truth value. False or not of false, that is false or true. This is again same by the very definition of the OR connective or operator. So what we got is, whatever the values that the atomic preposition P is assuming, this compound preposition, that is P or not P, is always taking true as its truth value. Hence this is a tautology. You understood? For whatever the combinations of atomic, for whatever the values that constituent atomic prepositions take, the compound preposition should always return true as its truth value. Then we say that particular compound statement is a tautology. Then we see another definition here, that is contradiction. We say a compound preposition is a contradiction if it takes always its truth value as false, immaterial of what its constituent atomic prepositions are assuming values. For example, we can easily see that if this is the compound preposition, whatever the values that P assumes, that is P can assume either true or false. In both the cases, this particular component statement always returns false as its value. Hence we call this compound statement a contradiction. So the all other statements, that is that means you have got a compound statement. If it is neither a tautology nor a contradiction, all such compound prepositions, we will call them as contingencies. Okay? We will say, if you have got a compound preposition like you have got a compound preposition P and another compound preposition Q, mind you, P, when I say compound preposition, it has got n number of constituent atomic prepositions which are connected by some operators. Similarly, Q, I say it is defined as P and Q are logically equivalent if and only if the compound statement that I get like this, P if and only if Q, if this is a tautology, I say P and Q are logically equivalent. Otherwise not. What I mean here is, I have got a compound statement P, another compound statement Q, and then I can construct another compound statement like P if and only if Q. If this compound statement is a tautology, then I say P and Q are logically equivalent, otherwise not. Okay, we will take an example and see how do we do it. And before that, I would like to go back and see how this operator if and only if has been defined in our previous lecture. If you remember, if P assumes false and Q assumes false, then P if and only if will take true as its truth value. This is how it is defined. Similarly, when P assumes false and Q assumes true, P if and only if Q takes false as its value. If you carefully observe, this P if and only if you, this compound statement assumes truth values, that is here and here, only when both P and Q will have the same values. That means if both values assume the same truth value, either false or truth, if both assume either false or truth, then this compound statement it takes truth as its value, otherwise not. Let us take this simple observation and we'll prove, we'll take two compound statements and prove that they are logically equivalent. Let us take two compound statements, that is P union Q. P or Q is logically equivalent to not P and not Q. Let us prove that these two compound statements, this compound statement and this compound statement are logically equivalent. As what we stated in the previous slide, to prove that these two compound statements are logically equivalent, what in fact we need to prove is P or Q if and only if not P and not Q. You consider this compound statement, and if this compound statement is a tautology, then we can confidently say that P or Q and not P and not Q are equivalent. Now let us find out the value of this compound statement. Okay. So now how many combinations, how many rows that our truth table will have, how many different combinations of values that P and Q can assume. One combination is P can assume false and Q can assume false. Another combination is P can assume false and Q can assume true, and these two are other two combinations. Okay. For each combination, let us try to find out what value that this particular compound statement takes, and if you are able to show that for all combinations of P and Q values, that means for all combinations of possible combinations of values that P and Q can assume, if this compound statement is always getting to true, then we can say this is tautology, and hence these two statements are equivalent. First, let us do it for when P assumes false and Q assumes false. Then P join P or Q is false, and then for all different combinations, let us find out the value of P or Q. It is by very definition of definition of R, how we defined in the last class. And let us find out what is not P. Let us find out not Q. This is also by very definition of the unary operator negation. Then let us find out what is not P and not Q. Is again by definition. When we find out when we find not P and not Q values, then what is not P and not Q is just apply not to this particular column. Not of T is false, not of false is true, not of false is true, not of false is true. That is how we found out. And now let us find out the value of this particular compound statement here. What I mean is, I am finding the value of this compound statement here. So what do you need to look? P or Q, and this particular columns you need to see. If you see in our previous slide, what we found out that if the value of P or Q and the value of not P and not Q is the same, then the if and only if operator is defined such that it takes true as its value. That is what we have seen in the last class, in the last slide. See this thing. See this thing, how it is defined. If you got a one compound statement, another compound statement, P in if and only if Q takes true as its value only when both assume the same values. In all other cases it is false. So similarly, now let us look at this. Now P or Q and not P and Q in the first row are taking the same values, so hence this particular compound statement will take true as its value. Let us come to the second row. Second row P or Q is taking true as its value, and this one not P and not Q is taking true as its value. Hence hence according to the very definition of the if and only if, we get true as its value. Third row it is taking true, both values are same, hence this particular compound statement will take true as its value. Fourth row P or Q is taking true as its value, and not P and not Q is taking true as its value. Hence this compound statement will take true as its truth value. If you find out now for all the combinations of P and Q values P and Q truth values, we found out that this particular compound preposition is always taking true as its truth value, which says that this compound preposition is a tautology. When we get this compound preposition as a tautology, according to what we saw in the previous slide, these two statements, that is P or Q and not P and not Q, these two statements are logically equivalent. That is how we prove logically equivalence of two compound statement using truth tables. If you can see, now there are a lot of laws that have been laid down in this prepositional logic, similar to what we have got laws, distributive law, associative law, commutative law in natural numbers. We do have the similar laws in prepositional logic also. Okay, let us see what are these laws, and they will be very helpful in proving the equivalence. We have proved using the truth table. There is another way that you can prove equivalence of two statements, equivalence of two compound prepositions, that is through the laws. We will see what are these laws, and these laws have got wide applicability. First law is P and true T is always equivalent to P. Similarly, P or false is always equivalent to P. This is the law. Another law that we have got is P or T, that is true, is equivalent to true, and P and F is equivalent to F, that is false. Idempotent law, P or P is equivalent to P. They are intuitively very much in line with our thinking. P and P is equivalent to P. Double negation, that is not of P is equivalent to P. Commutative, P or Q is equivalent to Q or P, and P and Q is equivalent to Q and P. Similarly, associative law, distributive law, this is P or Q and R is equivalent to P or Q and P or R. This is what De Morgan is responsible for this law. What it says is not of P and Q is equivalent to not of P or not of Q. Similarly, not of P or Q is equivalent to not of P and not of Q. This is what is De Morgan's law. This trivial tautology or contradiction is nothing but P or not P is equivalent to T and P and not P is equivalent to false. Now, though we have seen 5 or 6 operators like negation operator, OR operator, AND operator, exclusive OR operator, implication operator, if and only if operator. These 5-6 operators that we have seen previously, but one operator can be very well expressed in terms of another operators. We will see how they can be represented, how they can be seen. Exclusive OR, for example, exclusive OR P exclusive OR of Q is equivalent to P or Q and not of P and Q. What I mean here is, in fact, this whole operator is getting represented in terms of other operators like OR and NOT. That is what I mean here by one operator being defined in terms of other operators. This operator is being defined in terms of other operators. This is quite intuitive, isn't it? P exclusive OR actually is defined as either P or Q but not both. That is what exactly it means, either P or Q but not both. There is another operator like P implies Q. This is equivalent to not P or Q. This operator in fact can be represented as the combination of two operators, that is not and OR. Biconditional operator can be represented like P if and only if Q is equivalent to P implies Q and Q implies P. So now what we will do is, having seen how we can prove two compound statements are semantically same though they are syntactically different, this is what we have seen some time back. Using truth table, that is how we proved it. Now let us prove that these two statements, that is P and not Q implies P exclusive OR of R is equivalent to not of P or Q or not of R by using these laws. There are two ways that you can prove equivalence of compound prepositions. One way is using the truth table. How do you do it? For all different combinations of values that your atomic prepositions assume, your compound preposition always returns truth as its truth value. Then you say two compound prepositions are equivalent. What I mean is, if you have got two compound prepositions like P and Q, to prove that these two are equivalent for different combinations of values that P and Q assume, if I am able to prove that P and Q is a tautology, that means this compound statement of P and Q always takes true as its truth value, then I say P and Q are logically equivalent. This is how to prove by truth table. Okay, this is another way is, you take the left hand side, you take one compound preposition and you keep applying laws that we have seen some time back, like distributive law or associative law or De Morgan's law, and try to come to the right hand another preposition. Because all the statements that you have been using are equivalent, you can prove that your starting statement is equivalent to the destination statement. We will see how we will prove it. Let us take the preposition, the compound preposition P and not Q implies P exclusive OR of R. We will take this particular compound preposition, and finally by applying the laws we finally show that this preposition is equal to this preposition. Okay, we keep applying the laws. So we have seen that one of the law is A implies B. A implies B is same as, is logically equivalent to not A or B, isn't it? This is one law that we have seen. According to that law, this is A, this is B, not of A or B is that law. According to that law, we can write this statement is equivalent to this statement, isn't it? When we have got A implies B, that is equivalent to not of A or B. This is what the law says for us. Now what is A? This is A for us and this is B for us. So A implies B is not of A or B. So I just put that law here because hence that is the law. We say that these two are equivalent statements. Then by putting the very definition of the exclusive OR, what we get is P exclusive OR of R is same as P of P or R and not of P and R. This is by the very definition of exclusive OR. I can put this whole thing for this guy. So what is De Morgan law says is not of A and B is same as not of A or not of B. This is what De Morgan law says. I just apply De Morgan law for this guy, not P and not Q. When I apply that, when I apply De Morgan's law here, not of P and not of Q, I will get this guy. This is just by applying De Morgan's law. We have seen commutative law is nothing but not of P or Q is same as Q or not P. This is by commutative law. A or B is same as B or A. Hence you can write this. And because of the associative law, if you see, this is something like A or B or C. This is equivalent to A. This is equivalent to A or B or C. Similarly, this A, Q or not P or whole of this expression is equivalent to Q or not P or this. This is just an associative law application here. Now distributive law. This is like something like A or B and C, whereas B and C are in the bracket. A or B and C, which is nothing but A or B and A or C. I just put that here. I just put this associative law over here. Then this is where I put the associative law. Not P or R is equivalent to not P or P or R, but not P or P is same as true. This is again one law we have seen, trivial tautology, that is what it is known as. And whenever we have got true or any preposition or any preposition for that matter, here it is R, true or R is equivalent to true. This is what is domination law tells us. And again true and any other preposition is same as that preposition. Again this is because of identity law. So once we get this, again here we apply De Morgan's law to this particular portion, that is not of P and R is same as not of P or not of R. This is what is De Morgan's law that we apply here. Then we apply associative law. A or B or C is A or B or C. So we just apply associative law over here. This is again not P or not P is same as not P. This is what is idempotent law. So we get finally Q or not P or not R. And again, because of the associative law among these two, when we apply associative law, we will get Q or not P or not R. So again, by applying commutative law, we get this. This is what we need to prove. This is how we can prove logical, we can prove propositional equivalence by applying laws. One method we have seen thoroughly, that is how by using truth table we can prove that two compound propositions are equivalent. Another way to do is using these laws, De Morgan law, associative law, idempotent law and all. Okay. Thank you. Bye.